Welcome to the introductory lecture for EECE 320 lecture series. So in this video, we're not going to be going over much actual content. We're not going to be going over material, for instance, that would be useful for the homework assignment. But we are going to be doing sort of an introduction to the class and what we're doing and where we're going. And it's really important, especially in this class, to give a good idea of where we're going to go and why we're going to go there, because I think a lot of students will spend a lot of time working with OpAmps, learning how to do analysis with OpAmps, and never fully understanding why they are doing it. And so I think it's really good to set a clear expectation of why this is useful and what we're going to do that helps you do your job in the future as an engineer, and what we're not going to do. So it's just as important to say what we don't talk about as it is to say what we will talk about. So this background here, I have this nice salmon colored background. Years ago, I saw something that said that there was a test done of PowerPoint presentations, and they found that people, if there was a pink background to the slides, they retained the information better. So I'm going to do an experiment. This isn't quite pink, I guess. This is, I don't know. I'm not good enough with colorology to know what this is, but this is my color scheme I'm going with. The decision, I made the decision in about 3 minutes. So we're just going to stick with it all quarter. Sometimes you got to jump in with 2 feet. So this is EECE 320 electronics. We go over OpAmps mostly in this class. We also go over later on power conversion devices, power amplifiers, things like that. But for this first introduction, we're going to talk about what we're going to be doing with OpAmps. And this should be seen as, I'm going to try to sort of break this class up in the sense that I'm going to, when I assign a homework, I'm going to try to map the specific video lectures with the specific sections of the homework. Unfortunately, this one doesn't really map to any of the homework problems, but I will post it with that first homework. Also, this is probably the last time I'll refer to this as EECE 320 because I might want to reuse these videos. So I might want to use them after we change the class name. We change things all the time. As you know, this was not called EECE last year. So this is, I'll probably just not refer to it by name anymore, just so these videos are more applicable. And okay. So a little background on OpAmps. So why the name operational amplifier? Well, the name operational amplifier comes from the first usage of these types of amplifiers. It was discovered a long time ago that a high gain amplifier in certain topologies can be used to perform mathematical operations. And this is something you should have gotten from your review from earlier circuits class, from the review for ideal analysis of sort of the 4 standard op-amp cases, which are the inverting amplifier, the non-inverting amplifier, the summing amplifier, and the difference amplifier. We can configure op-amps to do these sorts of mathematical operations. And in the past, that was, I'm jumping forward. Sorry. I'm talking about all this stuff we're going to go over. We're going to go through each one of these questions slide by slide. So before I get too far ahead of myself, let's just go through all the questions we're going to talk about. So why operational amplifier? Why do we care about analog? This is a really important question that every class you take should answer. So nowadays, everything's digital. And a lot of schools still have curriculum that's heavily analog. And so it's, sometimes that's important. Sometimes the analog elements are still important and still relevant. Sometimes they're not. Sometimes the curriculum's just old and the people teaching it are just old and they don't want to change. And that happens too. But it should be justified. And so I'll do that in this class. I'll justify for why we still have this class, why it's still important. What should we consider for design? So this is the big thing is, what decisions do you need to make when you're doing an op-amp design? Where would you choose a different topology or a different amplifier? And then what's the future of op-amps? Where's op-amp technology going? And what components do we cover in this class? And then what don't we cover at the end? Okay, so going back to what I tried to jump right into in the previous slide, why do we call these operational amplifiers? Well, this was discovered a long time ago. That one of the coolest uses of these really high gain amplifiers is you could adjust the topology around that high gain amplifier and do all these sorts of nifty mathematical operations. So already inverting amplification and attenuation, non-inverting amplification addition and subtraction. You can also do integration and differentiation. And multiplication and division by constants can be done in the sense of, gain and attenuation, or sort of multiplication and division by constant value. So rather than by, two inputs multiply, that's more difficult. You can still do it, but that's a little more difficult with OpAmps. And so originally these were, when people had a complex mathematical equation, people would they would physically construct OpAmp circuits that had, I tried to find a picture of one, I couldn't find one. If you go through like any old math department, sometimes you'll see on the walls, they'll have these circuit boards that have just hundreds of OpAmp circuits on them. At the time, they probably cost $1,000 to build these things. And what they're doing is they're implementing complex mathematical equations with operational amplifiers, so that almost instantaneously, when your input changes, your output calculation changes. And they were able to do mathematical operations well beyond what you could do with digital back then. And so they had some use for that. Of course, now digital, we can do very complex math with digital systems fairly easily. So we don't have to use OpAmps for that particular use, but the core value of an OpAmp is still there. And that is, these high gain amplifiers are still extremely versatile. So we can still, by changing the topology, by changing the circuit around a very high gain amplifier, we can do all sorts of cool things. So even if it's not mathematical operations, we can still do neat things like take a high impedance voltage input and convert it to a low impedance voltage output. We can do things like amplify very small signals. We can do things like, once you get to AC analysis, filters and things like that. So we don't do that in this class, but there's all these kinds of things we can do that are at their core. We can do these because of the simplicity that results from having a very, very, very high gain factor in your amplifier. Okay, so why do we still care about analog? So many analog systems have been completely replaced by digital systems. There's entire fields of study that people used to do that they don't do anymore because they've become obsolete by digital technology. So why do we still care about OpAmps, these analog amplifiers? Well, because digital systems still have a challenge when it comes to extracting data from the natural world. So a lot of time, a digital system, one of the key things that a digital system does when it wants to take a signal is do an analog to digital conversion. And you've probably heard of those, you maybe use them. But analog to digital conversion still there's limitations to analog to digital conversion. You can't just, for instance, let's say you're measuring the voltage potential across a tree. Trees form this voltage potential that results from water flowing through the capillaries in their trunks. And people found a while ago, you can measure this voltage potential and you can see sort of how active and alive the tree is and how much water it's sucking up and how generally dry or healthy. I don't know all the stuff they find with it. I'm mostly made up what I just said there, but they can find things about a tree by measuring this voltage. The problem is this voltage signal is a very, very, very high impedance signal. This is like a 10 mega ohm impedance voltage signal, right? I mean, you kind of expect that. Otherwise, you could just use a tree as a battery and you could just, plug your iPhone into a tree and charge it. So it's clearly not it's not a low impedance voltage supply. It's a very high impedance voltage supply. And if you, for instance, if you took like a normal digital system and connected the input of the analog to digital converter right up to a tree, you'd get about nothing. Why? Because the input impedance of the analog to digital converter is going to be on the order of maybe a mega ohm, and this tree has an output impedance of 10 mega ohms or 20 mega ohms or 100 mega ohms. I don't know exactly what it is, and the other thing is the signal from the tree, you're talking about a voltage that's between maybe 0 and 100 millivolts, whereas the analog to digital converter on your digital system might have a range of 0 to 3 volts or 0 to 5 volts. And within that, it might only have 4,000 bits of resolution, 4,000 steps of resolution. So if you're looking at this 0 to 100 millivolt signal, you're going to get a very, not only are you not going to be able to read it because of the impedance issues, but you're going to have very limited resolution within it. And so normally what you would do is you would take that signal and you would convert it. You would both take it and convert it from a small voltage with a high impedance to a to a larger voltage with a low impedance. And then that's something that you could feed to an analog to digital converter. So that's kind of one example. A lot of times also we like to do an initial correction. So for instance, a lot of signals we get are differential. They go positive and negative. And digital systems don't tend to like negative voltages. So that's another thing. A lot of times if you have a signal, if you have a strain gauge and it produces a signal that varies between positive and negative 5 millivolts, a differential signal that is, that varies between positive and negative 5 millivolts, what you'd like to do sometimes is convert that to like 0 to 2 volts as something that a digital system can then convert using an analog to digital converter. And also, amplifiers have use even when dealing with digital signals themselves. So a lot of times digital signals, when they're transmitting a long distance through an environment, they pick up a lot of noise. And sometimes even we can take a digital signal and we can use an amplifier to remove noise that was added to that digital signal during transmission. And so sometimes even when it comes to just pure digital signals, amplifiers and op-amps still have some use. They still have things that we can do to help in that domain. So no, these are not obsolete. We'll still have these for a very long time. We'll still use these for a very long time. And so it's very important to still learn about these types of amplifiers. Where are op-amps used? Well, these are so versatile, they're basically used everywhere. So almost every single system other than just pure digital systems, almost every single system that interacts with the real world in one way or another is going to have an amplifier. And it's probably, if it has one, it's probably going to be an operational amplifier. And usually sometimes these are integrated into existing systems, so you don't always necessarily see the op-amp. Sometimes the op-amp circuit is sort of built into another circuit, even sometimes built into a digital circuit. But these are, and they're usually found at sort of the front and back end. So they're used to take some signal from the natural world, clean it up, amplify it, whatever, get it ready for consumption by another part of a circuit, or sometimes they're at the other end. They're the system that is, you've produced an audio tone and you want to amplify it to drive a speaker. Okay, well then maybe you'd use an op-amp for that. This example here is of a pulse oximeter. So this would be a portable battery powered device. And you can see in this, there are op-amps all over the place. So you see looks like 6 or so in here. So we have op-amps to use as a programmable current driver. We have op-amps that are used as the initial amplifier for the signal coming in from the pulse oximeter. So we're using the op-amp as a programmable current driver to drive these LEDs that shine light through your finger. We're using an op-amp to receive that input signal of the light that's transmitted through your finger. We're using an amplifier to filter. So we're using an amplifier to filter that. We're using an amplifier as a preamplifier for an analog to digital converter on a digital system. And we're using an amplifier to drive an alarm, a little tone signal on this pulse oximeter. So pulse oximeter, portable pulse oximeter, fairly modern device. They're not going anywhere. We still use them all the time. And we're talking half a dozen op-amps in the design of this particular system. And so this was a specific example because it's sort of mostly op-amps, but I'm trying to show this, right? These are used all over the place, still in very modern, very advanced systems, medical systems all over the place. So why medical systems all over the place is going back? Because medical systems nearly always interface with the human body. And so the human body is this big giant thing that exists in the natural world. And if we wanted to detect things about the human body, we have to measure them, right? So we're measuring resistances and impedances, and we're measuring pressures, and we're measuring volumes, and we're measuring, we're measuring chemical light absorption in the case of a pulse oximeter. And all of these measurements that we're doing, all these observations in the natural world, usually have some transducer at the front end that converts some signal to an electrical signal, and op-amps are involved in that process. And on the output too, right? So for instance, a speaker driver, we're taking a digital signal and converting it to a physical pressure wave that our eardrums are picking up. And again, that transducer, op-amps work at both ends, at the front and back end. And sometimes they work in the middle if we're doing lots of filtering and things like that. What should we consider for design? So this is really the big question is, why do we, it seems like we should be able to just sort of have a standard model for an op amp, right? You know, there's a limited number of things typically we want to do with them. We want to amplify signals, we want to offset signals, we want to convert currents to voltages, voltage to currents, things like that. There's only, you know, we could maybe list on a single page all the things we want to do with an op amp. And so it seems like we should just be able to just buy an op amp for each one of those applications, or we should already have it done. The design should already be done. And the problem, the reason we can't do that is because there's lots of parameters that matter. There's lots of trade-offs when dealing with these sorts of things. So, and we need to deal with a non-ideal. We could just spend a lot of money for like a nearly perfect instrumentation amplifier, which we'll talk about later, and that might work if you're willing to drop $20 on every single design, or on every stage of every single design. And so we're always dealing with trade-offs. We're dealing with trade-offs, non-ideal considerations, and trade-offs for mitigating those non-ideal considerations. So the types of things we have to deal with are high impedance voltage signals, low impedance current signals. Both of these are non-ideal. Very small signals, signals that are buried in noise, signals that vary by orders of magnitude. Let's say you're trying to measure something. Let's say you're trying to measure light intensity. Light intensity, you know, a very dimly lit room in the middle of the night, light intensity could be 6 orders of magnitude smaller than light intensity, you know, out on a sunny day. It could be 12 orders of magnitude smaller. I don't know. I'm making up the numbers as I go here. So, but there's many cases where you'd want to be able to measure light in all those situations. Let's say you have a cell phone and needs to choose how bright to make the screen. It really wants to know, are we in a very, very, very dimly lit room where somebody's eyes are probably adjusted to almost total darkness? Or are we, you know, in Arizona, you know, on June 21st on a, you know, 2 p.m. with blue skies, right? There's a big difference between those two, but we want to be able to know both. We don't want to just know, we don't just want to know, is it a cloudy day or a sunny day? We want to know, you know, is it pitch black in the middle of the night? Is somebody trying to browse on their phone, you know, under the covers while somebody else in the room is trying to get some sleep, right? And we want to be able to build systems that can adjust for that, and that can be very difficult to do. High frequency, high gain is another issue. So there's this, a lot of times the signals we get have to go up into the megahertz or maybe even the gigahertz range, and then we're talking, well, now we're looking at important considerations that we didn't necessarily look at when we were looking in the kilohertz or the hertz range, or the DC as this class. This class is basically just DC only. And then the big thing is everything comes at a cost, even cost. So what I mean by that is any one of these issues we want to correct, we have to buy a better version of op-amp to do that correction. And as we buy these better versions of op-amps that have better parameters and better features, that adds cost. And the problem is, if you're an engineer and you're working for a company that's building an actual product, the company has a strong pushback in the other direction that says, we don't want you to raise costs very much. We don't want you, you know, if you're building a pulse oximeter, you can't spend $20 for the op-amp to do that amplification of the signal, because now you're going to triple the cost of producing this pulse oximeter. And so the simple solution of just, well, you know, let's just, whatever, forget the cost, let's just get the best one we can and just always use the same design for every single application. Well, that runs into the challenge of this pressure you face as somebody making products that somebody else has to buy, in the sense that there's a cost to designing something with a high cost. If that, I kind of strained the language there for a little bit. Okay, now what is the future of op-amps? This is one of my favorite things to talk about, because, and this is one of the things that maybe when we're in an academic environment, we don't talk about this enough, but where are things going? So one of the biggest things that's happened in CMOS, or one of the biggest things that's happened in op-amps, is the switch to CMOS. So most op-amps use CMOS technology now. We've gotten very good at designing things using CMOS technology. It's driven down costs, it's driven down power consumption. And power really is the new axis of decision making. So going back to the pulse oximeter example, that pulse oximeter very likely was, you know, a lot of them now are these wireless digital devices that are battery powered, you know, sometimes just by a coin cell battery. And so if you're trying to have something measure, you know, blood oxygen concentration, and it's a wireless device that runs off a coin cell, well, guess what? You're probably not going to want to have an op-amp that just burns 30 milliamps of current all the time, like some of the older op-amps were. And so what you're going to do is you're going to say, I need to make a design, you know, if people need to switch out these coin cell batteries on my device every day, they're not going to want to buy it. They're going to go with a different company's product. And so one of the new axes of design, especially when it comes to portable electronics and wearable electronics, is power. So people start looking at problems in terms of how many joules is it going to cost for you to do this measurement? You know, how many joules is it going to cost? What's the price in joules of determining the blood oxygen concentration of somebody once? And then you can make other decisions about how many times do we do the measurement, or you can make other decisions about, you know, how many times do we need it to have it be clinically significant or something like that. But at sort of its core level, this sort of new dimension of op-amps that wasn't really a big deal 20 years ago is how much power they consume. So especially looking at sort of the constant power draw of these devices, not necessarily the power as things change, which isn't always as big of a deal when measuring like something like a DC signal. Okay, so also, you know, applications for op-amps have gone towards the portable, as I mentioned before, extreme low power. So again, the types of devices that can operate, you know, on a coin cell battery for a very long time. The scale, your bathroom scale. Have you ever noticed on a bathroom scale, you have to step on the scale usually to initially turn it on? Well, how does the scale do that? How does the scale know you stepped on the scale? Well, internally, a scale uses typically 4 load cells, and these load cells are basically just a piece of like a little twisted piece of metal with a strain gauge. So as you step on it, you compress the load cell, and the strain gauge picks up that strain. That strain is a resistance. It's a change in it shows up as a change in resistance. And so you have to have a circuit that takes that change in resistance and converts it to something that a microcontroller can read. Well, the problem is with a scale is you can't always, if you always have your measurement running, those 2 AAAs in your scale are going to be gone in an hour or so, right? They're going to, or not an hour, maybe a day. But you all know scale goes, you know, several months. So you can, you know, if it's the winter time and you're a little worried about seeing how many pounds you put on, you avoid stepping on that thing for a few months. And then it's beach season again and you decide to step on it, and lo and behold, when you push your foot on it, it still works. Well, how does it do that? It does have to be measuring. It has to be constantly measuring that load cell to detect when you're pushing your foot on it. Well, what's happening typically in a lot of these designs now is they have a special op-amp circuit that uses almost no power. So it does amplify the signal. What it's doing also is it's typically doing a differential measurement. So it's looking for that change, that slope of strain as your foot actually pushes or as your foot actually releases off the scale. And so it's this really just SIPs power circuit that measures this differential change in resistance. And once it detects that, then it switches back to, and it turns itself on and switches back to the normal operation of doing a more sensitive measurement to get the actual calibration and the actual weight and stuff. That's usually where you got to push on the scale and then step off it for a little bit until it says, okay, I'm calibrated and ready for you to actually weigh yourself. But these are the type of considerations that matter a lot, is how, you know, how low power can you make this for battery powered devices. Other important things for the future of op-amps is zeros. More and more measurements that op-amps are doing, including the strain gauge one that I just mentioned, operate near zero. So they're measuring signals that are very close to zero volt differential. Measuring very small voltage differences, extremely small voltage differences, means you typically have to have an op-amp that can operate with basically zero input bias. So it can have sort of zero voltage offset bias, zero differential. And it's actually very difficult to do that. It's very difficult to build op-amps that are able to amplify very small differential voltages. And there's a whole family of these. They do all sorts of crazy exotic things to cancel out little drifts and little offsets and little errors in these sorts of devices. And they can be very expensive, but this is another thing, sort of one category of the future of op-amps is cleaning up or is playing nice with zeros, with things near zero, of amplifying zeros. Also playing nice with ADCs. So most most designers of op amps now know, the output of my op amp is very likely going to be an ADC. And ADCs are typically multiplexed, and which means they do, as the digital system is switching the channel that it's measuring, it's taking the output voltage and charging and discharging, or it's charging a capacitor, and then it's doing a measurement on that capacitor. And so it's a little weird. If you're a device that's feeding a signal to an ADC, what you're seeing is something strange. You're seeing basically a very high impedance load, but occasionally, like 10,000 or 100,000 times a second, this thing is a very capacitive load. So it's this one microfarad or 0.1 microfarad capacitor or whatever they use to actually sample the digital signal, and that's strange, and that can lead to unusual, unexpected behavior in the output of an op amp. So a lot of op amps now are designed to basically, they're sold and they're geared towards being multiplexed for an ADC for a digital system. Also, a lot of op amps are going more application specific. So, and this is a big area. If you're somebody who sells op amps, as we mentioned in the previous slide, there's all these sorts of trade-offs with op amps. There's all these sorts of considerations. And an op amp, you might build an op amp that's really good at 3 of those considerations and really bad at 2 of them. So for instance, it might be really good at high gain. It might be really good to have a high gain bandwidth product. It might be really low power, but it might have a pretty bad voltage offset, or it might have a pretty bad current offset. So one of the things that, if you're a company that makes these op amps, that you want to do is you want to say, where are my strengths? What categories of measurement and design is my product really applicable? And then a lot of times what they'll do is they'll steer their sort of advertising towards those areas. So they'll usually define, hey, this is really good for doing load cell measurements, or, oh, this is really good at doing preamplification of RF signals, or, oh, this is really good at doing it as an audio driver, or something like that. So a lot of op amps now, just for market reasons, have sort of, they deliberately steer themselves towards one particular market segment or another, and they advertise themselves that way. And also, traditional parameters are always still important. So making everything better, all the traditional parameters like offset voltage, offset current, input voltage, input current, things like just the normal gain bandwidth product, linearity, high gain, all these sorts of things, low distortion, low noise. These are all these parameters that have been around forever. They're all still important, and they're all still getting better. So everybody sort of tries to make marginal improvements on these things, especially when it comes to using these CMOS devices. Low power CMOS devices, sometimes if you sell an op amp and that op amp consumes 1 microamp of current just by being on, that's incredible. And if you're able to achieve that, people will probably let you slide a little bit on some of these other parameters, because they're really looking for that op amp that sips power. But still, you want to make all those traditional parameters as good as you can. So what do we cover in this class? So this class goes over DC. So mostly what we're doing is we're doing conversion. So mostly what we're doing is we have an input. Your input could be a current. It could be a voltage. It could be a very small signal. It could be a big signal. It could be a negative signal. It could be a high impedance signal, a low impedance signal. And what we're doing is we're trying to design things that convert that into a signal that's more useful for us. And again, usually that's converted to something as the input to an analog to digital converter, but not always. So for this class, we're looking at DC analysis. We're not doing stability. We're not doing phase. We're not doing Bode plots and things like that. You'll do that in the follow-up to this class. So in this class, though, on op amps, we cover the ideal case. We cover non-ideal DC analysis using the control system model. So we introduce the control system model. You'll get a lot of control system model, and you can see the cover of the book that we use shows a sort of a control system model on there with feedback and feed forward. And so we use the control system model to do our analysis of these systems, forward gain, feedback gain. We look at non-ideal open loop gain. So we look at analysis with non-ideal open loop gain. That's mostly the sort of initial, the book talks about it, and then after they talk about it, they say, oh yeah, everything we just talked about we'll call that 2-port analysis. So we do sort of that. 2-port analysis is a bad name for it, I think, but that's what they end up calling it to differentiate it from from analysis that takes into account feed forward. So to differentiate it from that sort of return ratio type analysis, they call it two-port analysis. So we'll do that. We'll also do input-output resistance analysis. Sometimes that's really important, you know, especially when your input or output have strange features. You really want to know what your amplifier circuit, does your amplifier circuit have a high input impedance, a low input impedance? Does it have a high output impedance, a low output impedance? You want to know that sort of stuff. And then, you know, we might get to feed forward the return ratio stuff. We'll see. And then design topologies. So everything that I've talked about so far here is chapter 1. Chapter 2 is design topologies and considerations. Very important. Chapter 2 is like the keys to the vault. Chapter 2 is if you're working in a company and you want to build something that does this, how do you do it? What considerations are important? That's all chapter 2. Chapter 2 is like practical examples. Chapter 1 is like lots of math. We get stuck in the weeds of the math a little bit, which is important. Chapter 2 is really when it's like, hey, here's this thing you want to do sometimes. Here's how we build a circuit that does it. So chapter 2 is a lot more fun than chapter 1. We just got to get through chapter 1 together. What don't we cover? So just as important, we don't cover frequency analysis and stability. And I think I mentioned that already. I'm kind of jumping ahead of myself here. We don't go over the construction of OpAmps. So I showed it early on in the slideshow, 741 on the introductory slide. The 741 is like 30 transistors that make it up. We don't go over the actual internal construction of OpAmps. And it's just not really relevant to this class. If you were somebody who was designing OpAmps, it'd be relevant. It's not too, when you actually get into it, it's not that, it's usually fairly easy to see what the different sections are. If it's explained in a way that makes it clear, if you're just looking at a giant pile of transistors, it's like, what the heck? But when it's actually explained of, okay, this initial stage is an initial amplification stage. Here's another one that's a second amplification stage. Now this stage is to clean up nonlinearities, and then this stage is, you know, to whatever. You know, when it's explained that way, when you break it down into pieces, it's not so bad. When you just show somebody a pile of transistors, you know, just good night. Nobody's going to get that. So we don't go over complex system modeling. So you will do you know, more SPICE type analysis, more complicated control system analysis when you do control systems. We don't do much of that SPICE analysis here. We also don't do instabilities due to input and supply assumption violations. So this is an important one where sometimes you'll see these things show up as non-ideal effects if you're working for a company and you have a design and it's like, oh, my op-amp goes unstable every time I turn on this measurement thing. Well, sometimes you get weird stuff like your power rails weren't decoupled well enough, and so it created this instability and it created this weird critical pathway that went unstable. And coupling, you know, power supply coupling issues are rough. Usually the answer is just add more capacity or decouple the supplies more. We will mention sort of decoupling power supplies. That's an important general engineering concept. We don't go over it a lot though. We especially don't go over things like instabilities due to sort of you know, critical assumptions about the input supply path resistance and things like that. That's way beyond the scope of this class. We also don't directly do cost analysis. This is probably the biggest difference between what we do in this class and what you need for your career as an engineer is the nuts and bolts of what is it going to cost to go with option A? What's it going to cost to go with option B? What are the trade-offs? Can we correct those trade-offs digitally? The reason we don't go over it much here is because a lot of it is going to depend on the company you end up working for, or if you're working for yourself just based on your own design requirements. There's so many trade-offs to something like this. You know, sometimes the value of your time is big enough that it's worth it to just over design a system, go with an off the shelf solution you've already done. Sometimes that is actually worth it just to save yourself the time of having to redesign something. But these are tough decisions to make. These are business decisions, and this is not a business school. You might take business classes, but you're not going to find it here. So we'll talk about considerations that'll impact those decisions, but we don't directly do the cost analysis ourselves. All right, and that does it for the introductory video. Hopefully you enjoyed not having any math yet. The next video, we will have math. We'll jump right into it and we'll start doing working through some of those problems. But for now, welcome to the class. Welcome to the world of OpAmps.